Hello, Professor Scott Hubbard. This is my exam 2 video recording. I'll be doing problems 1, 5, and 4. So, to approach number 1, you have to look at it. We can see q of x does not equal 0, so this is a non-homogeneous. Zoom in. So this means that we have to solve for the particular solution, and we have to get the characteristic equation too. So let's do that first. And it's also a quadratic polynomial. Okay, so to get a characteristic, to get y sub c, we need to get y minus equals 0 and turn this to r minus 9. And here we have a difference of squares, so this can be written as r squared minus 9, r plus 3, and r minus 3. And we have real distinct roots, so our characteristic equation will just be in the form of yc equals c1 er1x, but we'll just sub it in right now, so 3x plus c2e, don't know what I should solve. Yeah, this will be our y of c, and to solve for a y of p, we need our trial solution for this will be, this is a quadratic polynomial, will be ax squared plus bx squared plus c. And we'll do that. So we need to first find the first derivative equals y sub p. Y sub p prime is equal to 2ax, take that out, plus b plus 0. Y double prime equals 2a plus 0, and that is our, we take these and we sub it back in. Let's do that right now. Let's sub it in. So just 2a, so then plus 9ax, so 18ax plus 9b equals x minus x squared minus plus x. After that, we have to match up the coefficients. This should be, I was looking at y sub p, so this should just be 9, just not y sub p prime. So 9bx plus c equals x squared minus, or plus x, 9c, and we have actually a negative here, okay. So negative negative, negative. Two 81. 281. 281. 281. Yeah, I think I made a mistake here. This shouldn't be negative, yeah, because A is the normal. Yeah, A just, B is negative, but yeah, okay. So our whole solution would be the y sub c and the y sub p solutions together, so it's supposed to be c1 equals c1 e 3x plus c2 e negative 3x plus, and then the trial solution we plug it in. So now we have a is 1 over 9 x squared plus 1 minus 1 9 x plus 281. And now for this, we have to find the constants. The IVPs are IVP 0, negative 1. Negative 1, so already is a 0, so negative 1 equals c1 to the 0 is c1 plus c2 plus 0 plus 0 plus and this will be c1 plus c2 minus this whole by minus the whole equation by 2 over 81, so this will be minus 83, 81 equals c1 plus c2. Seems like we have to do a system of equations here, so we will have then IVP2 y prime, I think y prime 0 equals 0. Y prime for this will equal 3 e to the x plus minus c2 e to the negative 3x plus 2 over 9 x minus 9 x plus 0. And if you do IVP equals 0 equals 3c1 plus negative 3c2 plus 0 minus 1 over 9. So now we plus this, so we get this on the other side. 1 over 9 equals 3c1 plus minus 3c2, and then times this by 1 over 3. Let's move this down. So what we will have now is 127 is equal to C1 minus C2. And we have a linear equation, so don't know. I'll just do this. $81, 1, 27. Let's do that. Minus R1. This will be 1101 negative 1. 83 of 81. Let's It's more scientific. It's 1.02 and 1 divided by 27 minus equals negative 987. Now we do negative 2 actually, so now we times this by positive, times this row by negative 1/2 actually. So let's have 1, 1, 2, 0s, 1 times 1 negative 493 plus, so yeah, and then we do minus R2. .002 minus equals 102 0.527. Okay, that is our constant values. This is C1, C2. Now we plug that into our whole solution now. So we have we have point 527 e to 3x plus plus 493 c2 e to 3x plus 19x 2 over 81. Ooh, that took too long. Yes, here's our solution, our full solution for the first problem. It could have done a linear equation, but or did it algebraically be faster, but don't know why I didn't. So here we have, let's do a free body diagram so we know what we're doing. So we have a steel ball, 64 pounds. And this is the equilibrium. So this is, say it's resting right here. This is the condition when the ball is on. Or when, here's the ball when it's like, it'll be self-explanatory. We have the IVP, which is, let's set into axis. This is positive, negative I. So this will be a negative IVP. It is 9 inches above 9 inches, which is 3/4 feet. So that's will be the IVP for number one for the spring equation. And since it's undampened, our motion of equation for undampened is mx squared plus kx equals 0. 0, and let's read this. So it stretches 3 feet. So that will help us find the spring constant. So spring constant, where Hooke's law is Ft, where force equals kx. So k equals the force, tension, divided by the distance. And here we have 64 divided by 3. That will be our spring constant K. And M, we need to get this in slugs, so slugs will be weight times gravity, which is imperial, since we'll be doing 64 divided by 32 equals 2. So let's write our diff EQ now. So 2 plus 64 over 3 x equals 0. For simplicity's sake, divided this by 1/2, whole equation. So we will have plus 32 over 3 x equals 0. So now we can do the quadratic to find the roots. So let's do this now. So r squared plus 32 with 3 equals 0. R squared equals 32 with 3. And since we can't take a square root of a minus, it will be a imaginary complex. So r equals square root of 32 over 3 I. We will now write our characteristic equation using this, and yc is equal to, since complex imaginary, 1c cosine square root 32 3x plus c2 sine 32 3x. So our IVPs now. IVP, we have IVP where it was initially at this point 9 inches above equilibrium. So those will be negative 3/4 equals 0. This will be our initial. And our second for constant 2 will be, so for our first, we have 0, 0, No, wait. It should be the other way. 3/4. So this will be if 3/4 is equal to C1 cosine of 0, because just multiply that by 0, and plus C2 sine 0. Sine 0 cancels out, or it's at 0 when it first starts. So this will be C1 is equal to -3/4. So for C2 now, let's get the derivative of this. So the derivative y sub c is C1 omega, just inside, negative sine omega plus C2 cosine omega and the inside function, or the angular frequency. So if we do the IVP again, the time with y prime is 0 is equal to 0. You can see that this cancels out. This has C1, which is -3/4, since the sine, it cancels out. And this has a value, so just say C2 has a value, but it's equal to 0. So C2 does not matter in this equation. So our equation of motion for this problem will just be the part with the first constant. So of motion equals -3/4 cosine square root 32 over 3 x plus 0, since constant 2 is 0, doesn't really matter. Okay, that should be the problem for answer for problem 2. Problem 3 is also another wave, or problem 4 is another wave problem. I need more space on here. One more page. This one, I want to see if, even though we did 5 first, this one is very similar. So as we can see, free body diagram, object weighing 6 inches below, so 6 inches positive. If we're doing plus x plus y, this will be IVP1, 6 inches, which is 1/2 feet, because we're doing feet. So no initial velocity, inches below its equilibrium point. So this one is also a undamped one, so equation of motion will be mx plus kx equals 0. So let's do this now. Let's first find the mass, which is in slugs, which is 4. Start as 2 inches, so 1/6 equals No, that was not right. Gravity in imperial units. So it'll be 1/8 is the mass. Spring constant is, spring constant. K is equal to F equals Kx. So K equals delta X over weight. No, other way around. So K equals Ft over X. So this will be 4 over 2 inches, 1/6 of a foot. Bring this up, equals 4 times 6 equals 24 is our spring constant, our resistance. So plug this in. 1/8 m 1/8 plus 24x equals 0. We want a whole number, so 1 times this by 8. 8x plus 24 times 8. 192 equals 0. We will use quadratic formula to find the roots. So R equals B plus minus over 2A zooming B squared minus 4AC equals no B, so 0 plus minus 0 minus 4 times 1 times 92 over 2A, and this will simplify to 8 square root 3I complex imaginary. Then our characteristic equation will be YC equals C1 cosine three x plus C2 sine x. After that, we have to solve for the constants now with the IVPs. So IVP initial y0 equals went down 6 inches, so 1/2. Then y prime 0 equals 0. We'll be doing a shortcut, but the derivative because it makes it simpler. So do 1/2 equals C1 cosine 8, or why am I multiplying this? Do 0 plus C2 sine 0, and C1 will equal 1/2. C1 equals 1/2. Now here's the shortcut we will do. We'll just use basic logic so you can save a bit of time. So if I get a derivative of this, or the derivative of this is product rule, which y prime will just, the part containing the C1 will turn to a negative sine x, and part containing C2 will turn to cosine x, and then we'll have inside function and times the inside function out here. Basically, when we look at it, when we do IVP, where y prime equal to 0, this will cancel out, even though we know the constant is 1/2 for C1, but this will just cancel out to 0. This will have a value, but it will be equal to 0. C1, so we can just disregard this part of the general equation. So our equation of motion for this part, for part A, part 4a, will be equation of motion will just be y equals 1/2 C1, that is C1 cosine 8 square root 3 x, and plus 0 since C2 will be 0. So find amplitude and period. So to find the amplitude is just this value right here, but since physics we did like the wave equation, so this will be the amplitude, and to find the period you take angle, this is the angular frequency, and to find the period it will just be period in seconds. It will be 2 pi over angular frequency. So let's find those. And then, since we're in period units, we'll just, our amplitude is equal to 1/2 feet, because we're in period units, and doesn't matter on time because they're always in seconds. Time, or it hurts me, I think it's in seconds. So time is equal to 2 pi. Okay, let's plug this in. There's no pi here. 2 pi divided by 8 square root 3, and 4.5 seconds. 0.45 seconds. That is the frequency, or that's the period. And problem 8 is, now we have a damping force. So here is the damping equation, or the undampened is plus kx equals 0, but for instead of a dampening force of 2 inches, this will be, we'll add a factor. So dampening is plus bx, no, okay, equals 0. So we have the same mass, I don't think that changed. 8 plus 2 plus, it was like 192. 192 times this by 8, so we have a whole number. So this will be plus 16 plus, that seems like a big number. Oh, it's 24. Stupid. And 24 times 8. 192. 2 equals 0. Now we do this. Do the same thing. We find the roots. 16r plus 2. Quadratic equation. So r equals 16 plus minus 16, 2 minus 4 times 1 times 192 divided by 2. This will simplify to negative 16 plus minus 256 minus 768 over 2. This one, 16 plus minus negative 512, and we'll have an imaginary number now because you have a negative there. So if we simplify it even further, we should have our roots to be negative 8 plus minus 8 square root 3. Square root 2 I. So, okay, let's do a characteristic equation now. So our y sub c is equal to, since we have here negative 8 instead of 0, what does it be? Because when you have no number there, it's just e to the 0, which is 1. So we'll have e negative 8 x times c1 cosine square root 2 plus c2 sine square root 2. So now let's find IVP. IVP is the 1/2 is 6 inches drop. P y 0 equals 6 inches, 1/2 feet. Okay. So 1/2 equals e to the 0 times C1 cosine 0 plus C2 sine 0. Sine cancels out, so we'll just have, like the first one, C1 is equal to 1/2. But like the shortcut we did for part A, we can't do that anymore. Because when we do a product rule, or we take the second derivative, first derivative will have a product rule, and the signs won't exactly cancel out, or C2 won't cancel out, and we'll actually have a value. So derivative of this is product rule is, okay, let's do -8 e to the x times C1 cosine angular frequency plus C2 sine angular frequency. Times C1 negative angular frequency, it's negative sign, plus C2 cosine angular frequency cosine. So this will be the IVP. So if we start plugging in numbers, so IVP 0 equals 0. We can see right here, this will go to 1. So right here, this will have value, so this will go to 1. This will be just e to the 1, so we'll have negative 8 times, since C1 is 1/2, this sign disappears. This sign disappears. So C2 equals C2, okay, plus C2 angular frequency is 2. Okay, so C2 2 is equal to -4. And now if we isolate this by dividing by 1/8 and multiplying by no, we divide both sides by 2, so C2 equal -4/8, so 1/2 over 2. This will be C2. So we can't do that elimination trick because we're doing a power rule, and it doesn't make it like clean to cancel out, or like the signs don't completely, or C2 doesn't completely get canceled out. So we have a C2 this time around. So the full solution with a dampening is added to a general solution. This cup here this is our solution from the first part A, but now we solve for C2 now. This will be 1, 2, 2 sine x. So that will be our solution for problem number 4, part C. Actually, no, not yet. Not the solution. Can't just copy it because these have different. You need to change these up first to have the proper angular frequency. So the right one is 8 square root 2. This should be the right one now because I didn't update it angular frequencies. So we solve for equation of motion with undampened, found amplitude and period, found a dampened case. This is similar to part 4A. We found undampened case. And we use matching of coefficients and some bit of linear algebra to get this solution. That is exam 2.